Welcome back to the second video for Tech 240 for Wednesday, March 3rd. In this video, we're going to start talking about a new topic, and that topic actually has a few connections to the previous topic, which was generators, as you'll see. But they are kind of a new and different thing, and I'm really excited to talk about motors because, motors, technically speaking, they're just pretty awesome to work with and to work on, and they enable us to do so many awesome things like electric vehicles, and HVAC systems and refrigeration systems and air conditioners and things like that, and lots of different applications of motors. And that gets to my second point. The reason they're good for us to talk about is because they're so important to our way of life and arguably becoming more and more important every year as more and more of our way of life gets electrified. We're having more and more reliance on the electric system year after year, especially with transportation networks increasingly being electrified. And how do all those things operate? Electric motors. They rely on electric motors of a bunch of different kinds. And so we'll talk about a whole bunch of different kinds over the next 3 weeks or so. So the first type of electric motor that we're going to talk about starting today are DC motors, direct current electric motors. And they're a little bit simpler and easier to talk about. So we'll start with those. The first thing we'll talk about today are the basic principles of operation and basically how a DC motor operates, the important things to understand about what makes a DC motor work. That'll be today. And then in our next class session, next time, we'll talk about what I call DC motor transients. What is a transient? Well, it means you're changing something. So it might mean that the motor is humming along at a constant speed, and then all of a sudden you change something. Or it might mean that the motor is stopped, and then all of a sudden you start it up. That's a transient also. So what do I mean by you change something? Well, for a DC motor, there's really only two things that you can change to a DC motor, while it's operating, and then you change something. Well, there's only two things you can really change. You can change the voltage that you apply to it. And of course, the voltage that we apply is a DC voltage. That's why they're called DC motors. So we can change the DC voltage that we apply to the motor, which is going to change something about its operation for sure. The other thing that we could possibly change about the operation of the motor is we could apply a different load to it, like an increasing load or a decreasing load. For example, let's say you're driving along down the interstate in your Tesla, and you're driving at a constant speed down the flat road, and then all of a sudden you start going up a hill. Well, that's an increased load. So now you're changing something about the operation because you're applying an increased load to the motor driving the wheels in your electric vehicle. Conversely, you could have a decreased loading on the machine by going along in your electric vehicle at a constant speed, and then you start going down a hill. So now there's going to be less load on the electric motor. So we'll talk about all those different things. What happens when you increase the applied voltage to a DC motor, decrease the applied voltage to a DC motor, increase the applied load, or decrease the applied load. That'll be our next class session. And then in the third and final class session on DC motors, we'll talk about several different designs of DC motors because there are a number of different common designs. One is the permanent magnet DC motor. That's the one that I suggest you start with if you are going to build your own DC motor for extra credit in this class. Don't forget about that. Let me know if you want to do that, and I'll provide you with materials. In addition to the permanent magnet DC motor, we've got series wound DC motors, we've got shunt wound DC motors, and some kind of combination or hybrid type motors. So we'll talk about the pros and cons of those different motor designs and applications and how those different motor designs work. In most semesters, the way I like to motivate this section of the course is by bringing my electric Harley-Davidson motorcycle into the classroom and just kind of showing all the different components on it, by showing the motor and the motor controller and the throttle, and talking a little bit about how the throttle controls the speed of the motor, showing the batteries. They're lithium iron phosphate batteries. There's 24 of them, about 4.5 kilowatt hours of energy storage. There's a battery management system that's on each of the 24 cells, of the battery pack, and that's monitoring the individual cell voltage of each one of those cells in the battery pack, and just kind of walking through it and showing it to you. I built it. It was right about 10 years ago now, so it's been a while, and it still works pretty well. It probably doesn't quite have the same range that it did initially, but it's still doing pretty well. Electric motors are very reliable pieces of equipment, so the motors will last a long, long time. But since I can't do that for practical purposes, what I'm going to do is show a video of an electric vehicle manufacturing facility that's just down the road. And I'm sure that you all know what that is. That's Rivian, which is only about 3, maybe 4 miles from where I sit right now. And I want to point out that they have a lot of jobs posted, both internships and full-time jobs posted on their website right now. So you should go check them out if you're at all interested in electric vehicles. That's a pretty awesome opportunity that's just in our backyard. I mean, it's pretty amazing. There aren't very many college campuses that have electric vehicle manufacturing plants 5 miles or less away from their campus. So that's pretty cool. So I'm just going to show you a video just to kind of get you, in the mood for talking about electric motors. All right, so here is one of their latest videos. All right, that's pretty cool. What I want to suggest to you is that do check out their careers page, because what I'm really hoping for is to develop a kind of relationship between ISU and Rivian, so we can set up things like internships, and maybe that would lead to more careers. And also, for selfish purposes, I would like to take a bunch of tours out there. I would love to take Tech 240 students out to the Rivian factory every semester and just take kind of a tour of the factory as an intro to talking about electric machines and motors. I think that would be a very cool thing to do in the future. So we're not quite there yet. They're not quite up and running yet. And for obvious reasons, we're not even in person right now. So can't do that this semester, but it's still a pretty cool opportunity that we have right in our backyard. All right. So with that introduction, let's go ahead and get started talking about electric motors. So to do that, I'm going to switch over to my document camera. All right, so here's what we've got so far. This is our DC generator, and we know it's a DC generator because you can see the split ring commutator right there. And we know that AC generators have slip rings, not split ring commutators. So we know that since this is a split ring commutator, we know this is a DC generator. But we know that if we apply our right-hand rule, we can find what the current flow is in this armature, because we're going to get an induced voltage. Remember, a changing magnetic flux induces a voltage, which causes current to flow. It doesn't induce a current directly. It induces a voltage, which causes current to flow. So we can go ahead and do that. Our motion, since this is rotating clockwise, our motion at this point in time of this side of the armature is up, and our motion of this side of the armature must be down, because this thing is rotating clockwise. So it's rotating around like this. So this must be going up right now, and this is going down right now. So if we apply our right-hand rule for generators, because we're told it's a generator, we have our field is going from left to right, and we have our motion on the left side of the armature is going up. So that leaves our second through fourth fingers going into the board or into the page. So my current is going into the page here. And then if I apply the same thing over here on the right side of the armature, my first finger goes from left to right. My thumb needs to point down, and that leaves, so I need to be like this. My thumb is pointing down, and that leaves my second through fourth fingers pointing up or out of the page. So the current is going like this. All right, so really the point, I mean, that was a nice little review, but really the point that I want to get at here is we have a relationship between the magnetic field and the charge or the current flowing through this armature and the movement of the wire. And in this case, in a generator, what we have is we have the magnetic field and we provide the motion, right? We provide this motion by rotating it clockwise. That's what a generator is. We have either maybe a steam turbine or a wind turbine or a natural gas turbine, a jet engine, something is providing this rotation of the armature, and that armature is rotating inside the magnetic field. And so as a result, we get induced voltage, and therefore we get current or flowing charge. We get charge to flow or current inside there. So we can see that those two lead to the third. The two being the rotation, the movement, and the magnetic field. If we have those, that leads to current flowing, leads to an induced voltage, which causes current flowing or flowing charge inside the armature. So the question might be, what if you applied the voltage and got a charge or current flowing inside the armature in the presence of the magnetic field? Would you in turn get motion? You see what I'm saying? We kind of got three different components. We've got motion, we've got flowing charge or current, we've got a magnetic field. In a generator, we're supplying the motion and the magnetic field, and we're getting the voltage and the current as a result. But think about this for a second. What would happen if we applied the voltage to the armature and therefore got current in the armature in the presence of the magnetic field? Would we then get the third thing, which was the motion? All right, so we're just kind of flipping some things around here. We're flipping the inputs and the outputs. In a generator, the input was the motion. In a motor, the input is going to be the applied voltage. And as a result of the applied voltage, we'll get current that flows inside the armature. And as it turns out, it's true. As it turns out, if you have an armature and you apply a voltage to it and you get current through that armature, and it's in the presence of a magnetic field, then you will actually generate not necessarily motion, but you'll produce a force. There's a name for that force. We'll talk about that in just a second. And if your armature is free to rotate, you know, if you're not holding it still, then that force is going to produce a torque, and that torque is going to produce motion. All right, so I know I just said a whole bunch of stuff. We're going to take it step by step here. So next I'm going to draw what is ultimately going to be a motor. So let's go ahead and draw a north pole. And then this is going to be a coil of wire, and I'm just going to draw it simply again with just one turn in it because that's simpler to think about. And then I've got my south pole over here. All right, and before what we had as an input, we had the motion. We had some kind of a turbine spinning this armature inside the magnetic field. But now in a motor, what we're going to do, let me label this DC motor. Now we've still got a split ring commutator, so I'm going to draw that again. It's kind of difficult to draw, but I just draw them as kind of like C's, mirror image of a C, and then the brushes are right here. So this is a brush and this is a brush. writing on that split ring commutator as the split ring commutator rotates around with the armature. Here's the brush that's stationary, writing on those rotating segments of the split ring commutator. And then over here, I'm going to apply a voltage. All right, so there's my voltage. And this is the positive side, and this is the negative side. And so as a result of that applied voltage, I'm going to get current to flow inside this armature. We know that current flows from positive to negative, so it's going to flow from the positive side through the split ring commutator into the armature, and it's going to be flowing this direction. And then it's going to be flowing around the armature and this direction. And back to the voltage source. All right. So what I was saying before was that if we have a current carrying conductor inside a magnetic field, what we actually get is a force. Now I'm going to define that force. So I'm going to write it out. What I'm going to write is there is a force produced on a wire. There is a force. We're going to name that force in a second. There is a force produced on a wire carrying current. There is a force produced on a wire carrying current inside a magnetic field. Inside a magnetic field. And the name of that force is called a Lorentz force. Spelled like this, L-O-R-E-N-T-Z force. So anytime you have a current carrying conductor inside of a magnetic field, there's going to be a force on that conductor. It's going to be pushing it one direction or the other. And the name of that force, the name of that push, is called the Lorentz force. Now we can analyze the Lorentz force either quantitatively with numbers or qualitatively with directions. And I'm going to tell you right now what the quantitative representation of the Lorentz force is, and then we're actually not going to use it again. So I'm going to call it F. I think you can see that. F sub L. That little arrow above the F indicates that this is a vector. A vector simply means something that has a magnitude and a direction. So the magnitude would be like a certain number of newtons or a certain number of pounds force, and it also has a direction. So it's acting in a certain direction that we are going to analyze in just a couple of minutes. So the Lorentz force is a vector. It has a certain amount of force acting in a certain direction, and that's a vector. So the Lorentz force is equal to the amount of current flowing through the conductor times the length of the conductor, which is also a vector, because the length has a certain magnitude. It might be 10 centimeters or 1 meter, and it has a certain direction as well. It's in this orientation or that orientation or so forth. And that is actually taken by the cross product. That's not actually a multiplication. It's the cross product of the magnetic field, which is B, which is also actually a vector because it has a magnitude, as in 1 Tesla, 2 Tesla, or whatever, and it has a direction, as we've seen lots of times so far. And the direction of the magnetic field is different depending on where in the magnetic field you are, where you're located. So this is actually the mathematical representation of the Lorentz force. I think you can see that, but I can't see it on my screen, so I don't know for sure that you see that when I have it down here. So this is the mathematical representation of the Lorentz force. However, the good news is we're not really going to use that equation in this class, and the reason for that is because this is not multiplication, this is a cross product. And cross product is not terribly difficult, but it does require linear algebra. And linear algebra is beyond the scope of this course. It's not a prerequisite for this course. So I guess you can say that we're saved by that. So we're not going to actually do any quantitative calculations of the Lorentz force. But I want you to know what the Lorentz force is. And I also want you to know qualitatively what direction the Lorentz force is acting in, which we're going to talk about in just a second. All right, so the direction of the Lorentz force, this is important for you to know. The direction of the Lorentz force is given by yet another hand rule. Don't worry, this is the last one. This is the last of our 3 hand rules. Remember, so far we've had the right-hand rule for current carrying conductors. We've had the right-hand rule for generators. And now we're going to have one last one, and that is the left-hand rule. So I'm going to abbreviate LHR for left-hand rule for motors. Left-hand rule for motors is the last of our 3 hand rules. And fortunately, the symbols, what each thing means, is really very similar to what everything meant with the right-hand rule for generators. So fortunately, it's not too difficult to learn the left-hand rule for motors once you've spent some time working with the right-hand rule for generators. So your thumb, once again, I want you to emphasize the M. And the thumb gives you the direction of motion that results from the Lorentz force. So this really is the direction of the Lorentz force. I say motion because, well, the mnemonic device works better with the M, and also because it's rotating. This thing is rotating. So typically, the armature is going to rotate. The rotor of the motor is going to rotate, given in the direction of the Lorentz force. So this is the direction of motion, which is caused by Lorentz force. You can also think of this as the thumb gives you the direction of the Lorentz force. That's also true. All right, so that was your thumb. Then you've got your first finger. This has not changed. Your first finger, think of the F sound in first finger. That's the direction of the field, the magnetic field, from north to south, same as before. And then your second through fourth fingers are, as you'd probably expect, the direction of current flow. So emphasize the C sound in second through fourth fingers. It's the direction of current flow. Direction of current flow. Direction of current flow through the wire or through the armature. Anytime you've got current flowing through a wire in the presence of a magnetic field, you're going to get a Lorentz force. All right, so we can actually apply that here. Let's go ahead and apply that to this case right here, since we've already got it right in front of us. So we want to know the direction of rotation of this motor. I want to know if this motor is rotating clockwise or counterclockwise. All right, so it's a motor, so I know I need to apply the left-hand rule for motors. And the thumb is what I'm trying to solve for. I need to solve for the direction of the Lorentz force, which is going to cause the motion which is going to tell me the direction of rotation. So thumb is what I'm solving for. The first finger tells me the direction of the field, and the field is left to right here. So my first finger has to point left to right. And the second through fourth fingers are the direction of current flow. So if I apply the left-hand rule for motors to this side, right here, the left side of the armature, I've got current going into the page like this. All right, so I would apply the left-hand rule like this, where my second through fourth fingers are going into the page. My first finger is aligned with the field from left to right, and then you can see my thumb is pointing down. All right, so the direction of the Lorentz force, I'm going to go ahead and write it F sub L. That's the direction of the Lorentz force on the left side of the armature is pointing down. Now let's do the same thing on the right side of the armature. My field is still pointing left to right, so my first finger points left to right. Now my current flow is coming out of the page, so I apply it like this. My second through fourth fingers are coming out of the page, and you can see my thumb is pointing up. So the Lorentz force on the right side of the armature is pointing up. So I have the forces aligned like this. And now, if this is free to rotate, if I'm not holding this in position or applying a brake or something on this, then that Lorentz force is going to cause a torque. And remember, hopefully you remember from TEC 111, the torque is equal to a force times a distance. And that distance is the axis of rotation. So let me draw that in. Use a different color. The axis of rotation is right down the middle. This is supposed to be pink, but it's looking kind of red to me. Looking like a pretty similar color to the Lorentz force. So there's the axis of rotation. So I have a force over here that's acting upwards on this wire, and a force over here that's pushing downwards on this wire. And I have an axis of rotation like this, so this thing is free to move in either direction. And if I have a force over here and a force over here, they both cause a torque. Remember, a torque is force times distance, and they both cause a torque in the counterclockwise direction. So as a result of that, this motor is going to rotate in the counterclockwise direction. All right, so we just did our first motor problem applying the left-hand rule for motors. All right, a couple things I want to point out. First of all, we talked about the basic requirements for generator action, and those basic requirements for generator action, hopefully you should remember them. We needed a conductor, we needed a magnetic field, and we needed motion between them in order to induce a voltage. And if we had those things, then we did induce a voltage. And if you had a complete circuit, then that induced voltage would cause current to flow. For motors, we can also talk about the minimum requirements for motor action or motor principle. And if you think about our previous discussion, there are actually only two requirements for motor action. One thing that you've got to have is a magnetic field. And the second thing that you've got to have is a current carrying conductor within that field. Current carrying conductor within the field. That's actually it. That's all you have to have for motor action. All right, so those are good things to know. You should definitely remember the 3 requirements for generator action, and you should definitely remember the 2 requirements for motor action. Those also are good things to remember that you might see on a quiz or an exam sometime. All right, so now I'm going to talk about a few practical applications of this, like how do we use some of this in the real world. So I'm going to draw another DC motor. Let me talk about this one. So we talked about the force, the Lorentz force that we get on this side of the armature and on this side of the armature. And clearly we get a force, a Lorentz force, that we can qualitatively talk about via the left-hand rule for motors. But let me draw a different situation. Let's say that same motor that I drew just a minute ago, let's say it came to rest in the position where its armature, or its coil of wire, came to rest in the vertical position. So let's say, here's my north pole. And what I'm going to try to draw, this is kind of tricky to draw, but what I'm going to try to draw is a DC motor with a simple armature, just one little coil of wire like we've been drawing, but that coil is vertical, all right? Whereas before we've been drawing it horizontal, but now we're going to think about what happens if our armature in the DC motor is vertical. All right, so that's what I'm trying to draw here. It's difficult to draw, but bear with me. Not totally sure how this is going to turn out, which is why I described what I was trying to draw before I actually drew it. And then let's say I've got a split ring commutator right here, and my brushes are right here, and I'm trying to apply a voltage to it still. All right, so there's going to be some problems with this. One problem that you might have identified right away, not the only problem, but one problem might be that my sides of my armature are in between segments of the split ring commutator. So I might actually have this side of the armature in between, on the top, the two sides of the armature, and on the bottom, it's hard to draw and hard to see with my drawing, but it might be true that this side of the armature is in between these segments on the bottom of the split ring commutator. So that might be true, in which case this motor would have a problem starting because we don't have any current flowing through there. But there's actually yet another problem. There's another problem. So let's say that we don't have this side of the armature in between these sides of the split ring. Let's say this side of the armature is still connected to the positive side of the battery. Really, you could say either side, but let's say, just for right now, let's say this side of the armature is still connected to this side of the split ring commutator, and this side of the armature is still connected to this side of the split ring commutator. So I've got current that's flowing into the page on this side, and I've got current flowing out of the page on this side. All right, so now I meet the requirements for motor action. I have a magnetic field, and I have a current carrying conductor within the magnetic field. All right, so I meet the requirements for motor action. But now let's go ahead and apply the left-hand rule for motors and see what happens. All right, so I'm going to apply it to the top wire, top side of the armature first. So left-hand rule, there's my left hand. The field is going from left to right. So my first finger goes left to right. And my current is going into the page. So my second through fourth fingers are going into the page. But now look where my thumb is. My thumb is going straight down. Straight down. That's F sub L. All right, so you might start to see a problem here. Let's do the same thing on the bottom side of the armature. So left-hand rule, my first finger is still left to right with the field, and my second through fourth fingers are coming out of the page because we have current down here coming out of the page. So now look where my thumb is. My thumb is going up. Thumb is going up towards the top of the page. So my Lorentz force is pointing down towards the axis of rotation on the top side, and it's pointing up towards the axis of rotation on the bottom side. And here's my axis of rotation that it's free to rotate about. It's free to rotate about that one axis of rotation via bearings and other things that we use to control the rotation, the split ring commutator, bearings and things. So it's free to rotate about this axis, but only this axis. And the problem here, if you think about the torque, once again, remember, torque is the force times the distance, and that's the distance from the axis of rotation. And if you think about what the distance is from the force to the axis of rotation, it's 0, because the force is going through the axis of rotation. So there's no distance between the force and the axis of rotation, because the force is going through the axis of rotation. So there is no torque in this situation. So if the motor, if our simple DC motor came to rest in a position like this, where the armature, we still call it an armature, where the armature was vertical as opposed to horizontal, then we have a problem, because we're not going to get any torque, and therefore the motor is not going to start. All right, so first of all, that's actually the reason. You might not have really known why at the time, but that's the reason why on your DC motor extra credit project, I told you you could get it started with a flick or a kick or whatever. You can get it started yourself manually, but then it has to operate independently. If you had a situation like this, if you had a really crude DC motor like this, then basically momentum is carrying it through this position up here. So once it gets away from vertical, then it will produce a torque again. But anytime the armature is vertical, it's not producing a torque. So first of all, I wanted to say that that's the reason why I'm allowing you to get it started manually for your extra credit DC motors. And the second thing is we want to avoid this situation, of course, in a real DC motor. So we don't do this design in a real DC motor. Instead, what we do, and this is even more difficult to draw, but you might be able to anticipate this. I don't want to have a situation in my DC motor where I don't have any torque. And so what I do is I start adding coils to the armature at different rotational points, right? So they're offset by a certain number of degrees, depending on how many sets of coils are on the armature. So I'm just going to add one set of coils and try to draw that, because that's hard enough to draw. All right, so here I'm going to add one set of coils, or I guess one coil, to the armature of this DC generator. So this one is horizontal. Maybe I should draw the other one in a different color. So the horizontal coil on the armature is horizontal at this point in time, and the vertical armature is purple. All right, so this is the hard part to draw. The hard part to draw is the connections to the split ring commutator. All right, so not bad so far. And my south pole's over here. And then I'm not going to try to draw this, but what you can see, you've got 4 different wires coming in, 2 wires from each coil on the armature. So our split ring commutator is going to have 4 segments like that. We've still only got 2 brushes. There's a brush, and there's a brush. And the brushes are connected to the DC power supply. I don't know if you can see that. Okay, so now the voltage is only going to be applied to one coil at a time, and it's always going to be applied to the coil that can produce torque. So in this, the way I've drawn it right now, and I know I haven't drawn these connections because it just gets tough to draw, but what we would have right now is that the applied voltage would be applied to the horizontal coil, which is the black coil, and it would not be applied to the purple coil. But then after this thing rotates by, say, 45 degrees, then now we're going to start applying the voltage to the purple coil, and the split ring commutator segments connected to the black coil are no longer going to be connected to the brushes. So this thing is going to rotate around, and we're going to alternately apply voltage to the black coil and then the purple coil, and the black coil, then the purple coil. As we rotate this around, our voltage will be applied to a different coil as this thing rotates, so that we're always going to have one coil in the armature that is capable of producing torque. So we're always going to get a Lorentz force that is aligned such that it can produce torque, and we can always have a starting torque. So we can always start the motor. All right, so in reality, you're always going to see a DC motor that has multiple coils. You'll never see a real DC motor that looks like this. All right, a couple more things that I want to talk about with regards to DC motors. Specifically with regards to controlling DC motors. All right, so the first thing that we want to talk about with regards to controlling DC motors is controlling just the speed. To control speed of a DC motor. To control the speed of a DC motor, well, you got to think about the Lorentz force, because the Lorentz force is what's causing the torque. And if we want to go faster, we need more torque. We need more torque to accelerate the motor to a faster RPM. So if we want to get a larger Lorentz force to accelerate the motor to a faster speed, remember what you got to have. You got to have a magnetic field. That's not going to change, but you also got to have a current carrying conductor within the field. So if you want to get a larger Lorentz force, then you need more current. How do you get more current? You apply a higher voltage. So the way you control the speed of a DC motor is by controlling the Lorentz force. But you can't control the Lorentz force directly. You can only control the Lorentz force by controlling the applied voltage, by controlling the applied DC voltage. So we can already say something about the transients that we're going to talk about next time. If I've got a DC motor and it's running along at normal operating speed at 6 volts, and then all of a sudden I apply 12 volts to that DC motor, it's going to result in more current through the armature, and that's going to result in a larger Lorentz force, and that's going to result in a larger torque that's applied, a larger motor torque, and that's going to result in acceleration of the motor and ultimately a faster speed of rotation of the motor. All right, the next thing is how to control the rotation direction. How to control the rotation direction. In other words, is it going to rotate clockwise or counterclockwise for a DC motor? How do you control the rotation direction? Well, if you think about your left-hand rule for motors, you know you've got your Lorentz force is your thumb, and your field is your first finger, and you're probably not going to be switching the field. Probably not. We'll talk more about that a little bit later. But let's say that you're not going to be switching the field. So the way that you're going to switch the rotation direction is by switching the current flow, right? Because if I switch the current flow from going down to going up, then I switch the direction of the Lorentz force from this way to this way, right? So the answer to that is you swap the polarity. But we're going to talk more about this in a little bit. I'm going to write this in a way that might not make sense right now, but I'm going to write this in a little bit more specific way. Ultimately, you know you're flipping the polarity of something. But what we're going to say is that we're going to swap the polarity swap the polarity of the current flow through the armature but we need to make it a little bit more specific, and you'll see why in a little bit, with respect to the field. All right. We're swapping the polarity of the current flow through the armature with respect to the magnetic field. And what I mean by that is if the magnetic field doesn't change, if the magnetic field is always pointing left to right, then it's true. All we have to do is swap the polarity of the applied voltage, and that'll give us a different current direction. That will flip the Lorentz force, which causes it to rotate in a different direction. However, in a couple of class sessions, we're going to talk about different kinds of DC motors. And sometimes when you just change the polarity of the applied voltage, that could actually change the direction of the field as well. And if you change the polarity of the field at the same time as you change the polarity of the current going through the armature, then it's kind of like taking a negative of a negative. If you take the negative of a negative, then you get the same thing. So we can't just say we swap the polarity of the applied voltage. We have to say we swap the polarity of the current flow through the armature with respect to the magnetic field. I don't know how much sense that makes right now, but in a couple of class sessions, we'll talk more about designs of DC motors like permanent magnet and shunt wound and series wound DC motors. I think it'll make more sense then. All right, the last thing I want to talk about right now before I switch over, and I've got a few slides I want to show you for DC motors. And the question that I like to lead with here is, let's say we've got a DC motor at rest, it's not spinning, and suddenly I apply a DC voltage, right? And the motor is going to start to accelerate. We'll talk about transients next time, but we can already say that if we apply a voltage, we're going to get a current to flow inside the armature. That current is going to result in a Lorentz force. That Lorentz force is going to give us a motor torque, which is going to cause the motor to accelerate, and it's going to start to spin faster and faster. But the question is that I like to pose is, let's say we got the motor, it's not spinning, we apply the voltage, and then the motor starts to accelerate. Will the motor accelerate forever? Will the motor continue to accelerate forever? I mean, the answer here is kind of intuitive, but the reason why is not. Will the motor continue to accelerate forever if applied voltage increases? All right, so I'm going to go back to our original drawing of a DC motor. And let's say that we applied this voltage right here. All right, so we applied this voltage right here. And when we apply that voltage, we get current to start flowing through here in this direction and then back this direction. And we already talked through this. We had a Lorentz force that was acting down on this side, up on that side. So that created a torque in the counterclockwise direction. And so this thing is going to start to rotate in the counterclockwise direction. All right. So now the question is, what's limiting that acceleration? Is this going to continue forever? Is it going to accelerate in the counterclockwise direction forever, indefinitely? And usually the answer that I get for that is no, because there's air drag, there's resistance as this armature is rotating around, there's drag from the air. There's also some resistance in the bearings. There might be a bearing over on this side and probably a bearing on this side too, or a bushing or something. And there's drag and resistance there too, so that's going to limit the RPM. And that's not totally wrong. It's true, there's some drag, but there's actually something that is a lot more significant. There's a lot more significant than the drag. And so to do that, I want to think through what we've got here. So once we've got motion, once this thing is actually rotating, what we have a conductor, we have a magnetic field, and we now have motion. We now have motion between them, right? So think about what that means. If we have a conductor, like here, you know, who cares if it's in a motor, but who cares? We've got a conductor, we've got a magnetic field, and we've got motion between them. What does that sound like? And hopefully that's ringing a bell right now, because those are precisely the three requirements for generator action. Not motor action, but generator action. And so as this motor starts spinning faster and faster, I actually meet the requirements for generator action. So I actually have generator action happening inside of an operating motor. Furthermore, let's go ahead and apply the right-hand rule, because I know I have generator action happening inside this motor. So let's go ahead and apply the right-hand rule and see what the polarity of the induced voltage is as this motor starts spinning faster and faster. All right, so I'm going to apply the right-hand rule for generators to this motor as this motor is spinning, right? So we don't have generator action until this motor starts spinning, and spinning pretty fast. All right, so first I'm going to apply the right-hand rule to this right side of the armature. So right-hand rule, the field, first finger is going left to right, and direction of motion, this thing is spinning counterclockwise, right? So the direction of motion right now is up, all right? So I apply my right-hand rule. My first finger is the field, it's going left to right, and as this thing is rotating counterclockwise, this wire right here is moving up. So in my right-hand rule, the thumb is the direction of motion, right? And then my second through fourth fingers, which are right here, they give me the direction of current flow as caused by the induced voltage. And they're actually going into the board, right? So my current flow as caused by the induced voltage is actually going into the board. So I'm gonna draw that in purple. So what I actually would get, I'm gonna call this I sub, and there's a term for this. I'm going to go ahead and write it down. I haven't mentioned it yet, but it's called counter EMF. I'm going to abbreviate it C dot EMF. EMF is just voltage. So what this generator action inside of a motor, a spinning motor, is called is counter EMF. It means counter voltage. And what that means is that the voltage that's induced actually opposes the current flowing through the motor. Right, and we could apply it to this same, this other side over here. So my field is from left to right, and my motion is down. Right, so first finger goes from left to right, and the motion, this thing is rotating counterclockwise, so my thumb faces down, and then my second through fourth fingers are pointing down towards the bottom of the page. I hope you can kind of see that. So this arrow is going to be going out of the page like this. So this is the current that would result from the induced voltage, or the counter EMF. All right, so that is a pretty complicated subject, and I expect that was difficult to follow, but let's go ahead and write something down about counter EMF. So what we have, so the answer to this The answer is, will the motor continue to accelerate forever if the applied voltage increases? The answer is no. It's not going to increase forever. And ultimately, the reason is because of counter EMF. So what we have, so as the RPM increases, so as the motor starts spinning faster and faster, we have a conductor, we have magnetic field, and we have relative motion between them. Relative motion between them. All right, so what this means is we have the requirements. We meet the requirements for generator action inside a spinning DC motor, or any motor actually. All right. And furthermore, we know we meet the requirements for generator action, but then we can apply right-hand rule for generators. Generators, sorry, not generations, generators. And we see that the induced voltage caused by that generator action, induced voltage caused by that generator action that we just talked about, that actually opposes the applied voltage, the initially applied voltage. And then we have a name for that, and we call that counter EMF. Counter EMF. That's an important concept, the concept of counter EMF, how we have generator action inside of an operating motor is an important concept to understand. And that's actually what limits the RPM of a motor. So no, the motor's not going to spin up and accelerate to an infinite speed. There's going to be this balancing act, this balance between the current that's going through the armature caused by the applied voltage. That was this voltage right here. So we have a current through the armature as a result of this voltage applied right there. But then we also, once this thing starts spinning faster and faster, we get an induced voltage that's caused by generator action due to these requirements, due to meeting these requirements, and that induced voltage opposes the applied voltage. So when these two are going to balance out, then we're going to reach a steady state. And we'll talk more about that in a little bit. Next time, actually. We'll talk more about when these things balance out and reach a steady state. But the reason that they do balance out is because of this principle, because of counter EMF. All right, that is the vast majority of the content material for today. I do have a couple of slides just to reinforce some of these concepts and get us ready to talk about DC motor transients next time. So I'm going to bring up my slides. All right, I'm just going to start going into the first 6 or 7 slides of the DC motors presentation, and that way we will be all set to start talking about transients in the next class session. All right, so first of all, a review of the terminology, because it's just a little bit different than generator terminology, all right? We've still got our physical components, and we've still got something that is rotating, and we've got something that is stationary. And we call the rotating thing a rotor, and we call the stationary thing a stator. So that hasn't changed from when we were talking about generators. Normally, when we're talking about DC motors, I mean, almost always, the rotating thing is on the inside, and it's rotating around on the inside, and the stator is on the outside. And typically, we have the coil of wire, which we call the armature. That's going to be on the rotor. So we've got our armature is going to be rotating on the inside, and our magnetic field is going to be stationary on the outside. So that's pretty much the way that almost all DC motors are constructed. You know, whereas with generators, it's kind of like, you know, whatever goes, you know, like you can make generators in lots of different configurations. And admittedly, that makes them, you know, maybe a little bit more difficult to learn because there's all different possible configurations for generators. But with DC motors, it's pretty consistent. Your armature is going to be on the rotor in the middle, rotating around, and your magnetic field is going to be on the stator around the outside. All right, so mechanically or physically, we got the rotor, we got the stator. Electrically, they're pretty similar. We've still got something called an armature. And remember before with the generator, the armature was where the voltage was induced. And then we had to use either slip rings in the case of an AC generator or a split ring commutator in the case of a DC generator to get the voltage off of the armature and transfer that electricity or the current from the armature to the stationary electric grid, right? So in a generator, the armature was where the voltage was induced, but now in a motor, the armature is where we're applying the voltage to. So we've got a voltage source, and in the case of a DC motor, it's a DC voltage source, like a battery, and we're going to be applying that DC voltage source through a split ring commutator to the armature. So we're going to cause current to flow through the armature due to the applied DC voltage. All right, so that's the armature. The field, we still got to have a magnetic field. We still could create our magnetic field either with permanent magnets or with electromagnets. And in a couple of class sessions, we're going to talk about different designs of DC motors, and we'll talk about both. How you could create them with permanent magnets or how you could create them with electromagnets, because both are actually quite common. All right, so that's a little bit of terminology. Here is the basic construction of a DC motor that I just tried to draw, but I can't draw quite this well, so this is a better picture to look at. So right here, we got our voltage source down here. And then we've got our brushes on either side here of our split ring commutator. Here's our split ring commutator. It's divided up into lots of different sections. And then here is our armature right here. And you'll see a bunch of coils of wire on the armature. And the reason is, like we just talked about a little bit ago, we want to make sure that we've always got at least one coil on the armature that is producing a high amount of torque. All right. And in real DC motors, generally you'll have at least a dozen or so coils on the armature. So when I drew it a little bit ago, the most complex one that I tried to draw was an armature with 2 coils on it. But in real life, even the smallest DC motors that you'll find, and in fact, we will dissect a very small DC motor in one of the upcoming labs. Don't remember which one, but in a soon-to-be upcoming lab about DC motors, we're actually going to dissect. We're going to take apart a DC motor, and we'll look at how it was put together. So anyway. In even the smallest DC motors, you'll always see at least 3. That's the smallest I've ever seen, is 3 coils of wire on the armature. All right. So this is the drawing, and the only thing I didn't say was the magnetic field. So in this case, it's a permanent magnetic field on the stator that's providing the magnetic field, but it could certainly be electromagnets. You could have coils of wire on this side and on this side, and then apply a DC voltage to those coils of wire, and then that creates an electromagnet, and now you've got a magnetic field that way. So it doesn't matter whether your magnetic field is caused by permanent magnets or electromagnets, you just need to have a magnetic field. And here's a picture of the rotor of a DC motor. Split ring commutator right here, you can see all the individual segments. And then here is the armature with all the coils of wire on it. All right, we talked about this, but quick review here. The minimum requirements for motor action, which is another way of saying the minimum requirements that you need to create a Lorentz force, because that's what motor action is. It's a Lorentz force. So to create a Lorentz force or motor action, you got to have a magnetic field, and you got to have a current carrying conductor within that magnetic field. And if you have those, then you will cause a Lorentz force on that wire. And if you set up your wire in a clever way, such that it can rotate around a central axis, then you will create rotation. And we can use that rotation to drive gearboxes and to drive conveyors and drive motors and drive electric vehicles and all kinds of other things that electric motors are used for. All right, once again, don't forget your left-hand rule for motors, where your thumb gives you the direction of the motion of the wire at that point in time. That's also the direction of the Lorentz force. Your first finger gives you the direction of the field from left to right, always pointing in the direction of the field. And your second through fourth fingers are giving you the direction of current flow, all right, through the armature. All right, so I'm actually in this slide going to kind of lead up to transients, but we're going to stop before we really start talking about transients. So just think through this. What happens when a motor is stopped? All right, I've got a motor and it's not rotating, and now I apply a voltage to it. All right, so I apply a DC voltage to the armature, so I get current to flow through that armature. And of course, that armature is inside of a magnetic field. So if we have current flowing through a conductor inside of a magnetic field, then that meets the requirements for motor action, which gives us a Lorentz force. So if we get a Lorentz force on the armature, and that armature is free to rotate around a central axis, then that's going to create a torque on the armature. And the torque is the force, which is the Lorentz force, times the distance, which is the distance from the central axis to the Lorentz force. It's just like any other torque, you know, a wrench. A torque on a wrench is equal to the length of the lever arm of the wrench times the amount of force that you're applying to that end of that lever. So it's the same idea here. The Lorentz force gives us a torque that is going to cause that armature to start to rotate around its central axis. All right, so now our motor has started rotating. All right, so it's starting to rotate, and I've got that Lorentz force, so it's going to accelerate. But this is what we just talked through a minute ago. Is it going to accelerate forever? No, it's not going to accelerate forever, because once it starts rotating and once it starts spinning faster and faster, what have we got? We got a conductor, we got a magnetic field, and we've got relative motion between the two, which gives us generator action. So we actually have generator action inside of our operating motor. And if we apply the right-hand rule to that generator action that is being created inside that motor, what we find is that the voltage caused by the generator action, the induced voltage, is trying to cause current to flow in the opposite direction that the applied voltage is trying to cause current to flow through the armature. All right, so the generator action, the induced voltage caused by generator action opposes the applied voltage that we're using to try to get the motor to spin in the first place. All right, so that generator action inside the motor, we call that counter EMF. And these two things are fighting. The applied voltage and the counter EMF are fighting. And so what the armature really feels is the difference between the two. What the armature is feeling, the voltage the armature is feeling, is the difference between the applied voltage minus the counter EMF. Here's a little maybe clarification. The counter EMF is never going to exceed the applied voltage. never going to exceed the applied voltage, but they will be very close. They will be very close when they're at steady state, which means the motor is neither accelerating nor decelerating. All right. So, speaking of steady state, the motor is going to reach a steady state operation. That means a steady operating speed where it's neither accelerating nor decelerating. It's going to reach a steady operating speed when the motor torque, which is caused by the Lorentz force, which is caused by the armature current inside that magnetic field, which is caused ultimately by the voltage that is felt by the armature, when that motor torque is exactly balanced by the load torque, which is caused by whatever the motor is driving. You know, it's caused by the car going up a hill, or resistance from the conveyor if it's driving a conveyor. Whatever it's driving, whatever the motor is driving, that is the load. So whenever the motor torque is exactly balanced by the load torque, that's when it's going to be in steady state operation. All right, so what we've got, I'm going to stop here, but what we've got is a feedback loop. All right, so we're going to apply a voltage. That's going to cause current to flow. That's going to give us a Lorentz force. That's going to create a torque. That's going to cause it to accelerate. That's going to cause the RPM to increase. That's going to cause the counter EMF to increase, and that's going to reduce the voltage felt by the armature, which is going to bring down the armature current, which is going to bring down the Lorentz force, which is going to bring the motor torque down such that it's more in line with the load torque, which is going to cause the acceleration to decrease, which is kind of cause us our RPM to approach a final steady state condition. All right. I don't want you to necessarily rack your brain over that right now. That is called a motor transient. And we're going to talk a lot more about that next time. I just wanted to introduce this and the idea that it is a constant feedback loop. And this is really happening instantaneously all the time. This is a constant feedback loop that is being felt and experienced by the motor all the time. And we'll talk more about the specifics of motor transients and what happens when you alter something about the motor, like you suddenly increase the voltage or you suddenly decrease the voltage that you apply to the motor, or you suddenly increase the load that is applied to the motor, or you suddenly decrease the load applied to the motor. We'll talk more about that in the next class. So for now, I think that's going to wrap things up for this video. I will make a recommendation. Transients are a little bit challenging. They're one of the more challenging things, I think, to understand in this section of the class. So I would highly recommend that you read the section in the lab manual about DC motor transients. And I think that section, well, which section is that? Oh, it looks like it's part 4 of the lab manual. I'm just looking at the reading assignment. So read the section in the lab manual about DC motor transients, and trust me, that will make next class session go a lot smoother for you. All right, so that's going to wrap things up for today. Let me know if you have any questions, and I'll see you next time.